Thanks. In the interest of pressing on towards coffee break, we'll just defer questions until the coffee break, or we have time for a discussion. Our next speaker is Dr. Sarah Muldoon, who is at University of Pennsylvania now and will soon be a faculty member in Buffalo. So, thank you.
All right. So, thank you so much for having me today. I'm Sarah Muldoon. I should say that for what I'm going to talk about, many of you are probably more familiar with my current advisor named Danny Bassett. So we do a lot of network modeling of fMRI data in our lab, and we're specifically interested in looking at multi-layer dynamic networks. And so that's what I'm going to talk to you about today. So this is actually not the beginning of my talk. All right. We're going to go back a lot. Sorry, everyone. Okay, so here's the start of the talk. All right, so moving forward. All right, so there's been a lot of recent interest in looking at measures of dynamic connectivity because there's the realization that interactions between different areas of the brain evolve with time as we're doing different tasks or in different states. And there's a lot of different ways you can study the dynamic nature of the brain, and I want to say that I'm just really going to focus on one very specific way of looking at this today, and that's using network analysis. And I'm going to talk about some new mathematical frameworks that you can use specifically to look at the evolution of networks over time. All right, so here's kind of an outline of what I'm going to talk about. First, I'm just going to review some of the basic principles of the things we want to look at when we build fMRI networks. And then I'm going to introduce a new mathematical formalism that people have been using called multi-layer networks. And I'll talk specifically how we can construct these types of networks for task data and for temporal data. And I'll go through some statistics that you can use to measure the changes in network structure over time using this type of formalism, and briefly show some applications to data. I should say that throughout my talk, I'm going to hopefully have references on the slides. I encourage you to download the slides and look at the references to go into depth into some of the methods that we use, because I won't have time to discuss everything in detail. But hopefully you'll find the references useful. All right, so first of all, I just kind of want to review how we go about building networks from fMRI data. So for the talks that you've been listening to previously, people have talked a lot about how to extract the bold signal from the data. For everything I'm going to talk about today, I'm going to assume you've done all of that, and we're starting with time series of the bold signal that you've extracted from the data. And now our goal is to take those time series and turn the representation of the brain into a graph. And so when we do that, we're going to build a graph, and the graph has two basic components. We need to define nodes of the graph, and we need to define the edges that connect our nodes. And this is what we're going to use to study. And we can represent that in what's called an adjacency matrix, where here you can see a filled-in square is going to indicate a connection between two nodes. The nodes are the axes of the matrix, and the color of the square here represents the strength of the connection. And so this is how we visualize a lot of data when we're looking at these functional networks. All right, so to do this, though, we have some choices that we have to make, because we need to define what the nodes are and what the edges are in these networks. And so when we define the nodes, we can do this in many different ways, and a lot of that depends on the choice of scale that you want to look at. So you can think about this. You could look at individual voxels, and you can consider each voxel to be a node of the network and ask about relationships between voxels. You could think about a little larger scale, looking at anatomical atlases. Maybe you parcelate the brain into some sort of region, group of regions based on anatomical knowledge, and then ask how the signals from different regions relate to each other. You could also use functional boundaries to look at nodes. And then in all of these cases, you can also talk about the parcellation scheme. So let's say you've chosen an anatomical atlas. You could say, well, what if I break it down into smaller and smaller pieces? And what happens as I change the spatial scales of the regions that I'm looking at? And so for simplicity in the rest of what I'm going to talk about, I'm going to just refer to the nodes of the network as regions and assume that you've done some sort of parcellation based on anatomical regions or something like that. But be aware that the choice is yours of how to do this, and it's going to depend on the types of questions you're interested in looking at. The next step in building these networks is that you want to have some basic idea of how you're defining edges. So generally, we build undirected networks where we're just looking at statistical relationships between the activity of brain regions. And common ways to do this are looking at measures such as correlation, coherence, wavelet decomposition. And basically, you're just measuring the statistical relationship between the activity patterns of two brain regions. You can also look at some sort of directed measures and what's called effective connectivity. For what I'm going to talk about, we're just going to talk about undirected networks, though, where we're just looking essentially at correlations between the time series of brain regions. All right, so there's also some other things you should take into consideration when you're looking at these edges, and there's different ways of analyzing your signal. So maybe you're interested in only looking at a certain frequency band. So you could bandpass your signal, and you could then work in the time domain, or you could choose measures to calculate these statistical relationships that are already frequency dependent, such as coherence or wavelets, and look over the frequency bands that you're interested in. Also, when we're measuring these statistical dependencies, you're going to have some sort of weighted measure of strength in these networks. And so sometimes what people do is they say, well, I'm only going to look at interactions that are greater than some level. And they threshold the networks and turn it into a binary network where you say there's either a connection or not between these two brain regions based on the strength of the relationship between them. And I just want to say that this is something that you can do, and a lot of reasons for doing it are that the math you want to do later to calculate the measures of network connectivity only work for binary matrices, but you should also be aware that thresholding can potentially throw away some important information, and there's evidence showing that sometimes these weak connections that you might throw away are actually predictive of some of the things you might be interested in. Specifically, there's work showing in schizophrenia, the weak connections actually were predictive of the progression of the disease, not the strong ones. So you need to be careful when making these choices of how you're going to build the networks and take into consideration some of the things that you might be interested in looking at in your system. All right, but what we're really interested in today is studying the dynamics of these networks. So we know that a lot of cognitive processes are dynamic. You can think about this in terms of memory, learning, attention fatigue. There's really lots of different things you can talk about and want to study how the network structure changes as a course of time as our cognitive processes evolve. And so what we're going to look at is measures of building networks that we can study throughout time and look at the effects of different tasks, or maybe look at how the structure of the network evolves as you learn a certain task, or as you age, or as the disease progresses. All right, so in order to do this, I'm going to talk about this new mathematical framework that's been developed called multi-layer networks. And here's kind of a general introduction to the concept. Basically, what we've talked about is, in building these networks, is some sort of static picture of the system. And so you can think of that as a single layer in this. So if you had a functional connectivity matrix where you've looked at pairwise correlations, that's going to be represented in one of these single layers here. So each layer can have nodes in it, but we can also have different types of interactions between nodes. So let's say that, actually I'm just going to switch to the next slide for a more discrete example of what this works. So this is just kind of a generic example looking at a system of network scientists. And so in this case, the green layers here, this is 3 different conferences, and it's 4 different people at 3 different conferences. So this kind of gives you a general idea of how you would set up something in a multi-layer framework. So here's the nodes, and each layer is going to contain its own network. So here we have 3 scientists that were at this network, and in this layer here, the edges within the layer represent an interaction of the scientist talk to the other scientist. However, in this layer over here, the connections between nodes here represent that they went to a talk by the other. All right, and so then these dashed lines in between just tell you that this scientist here is the same in both of these networks. So it gives a sense of identity, a way of linking what node is what between the 2 networks. And then we can also do the same thing for a second conference. And you can see here that in this case, the same 3 scientists were at the 2 conferences, but at this third conference over here, one of them wasn't present and a new scientist was. And we can take those types of interactions into account by building our network in such a way where we have different types of interaction in our different layers, different points in time going along the vertical axis, and we link identity of the nodes between all the layers so that we can keep track of who is who in each instance. All right, and so what this does is lets us build, it's a very flexible framework, and it lets us build many different types of networks that we can then study. So I told you that we were interested, though, in studying dynamic networks, and so we're really interested in this aspect of time in the networks. So to do that, we can kind of think about a little simplified version of a multi-layer network called a multiplex network. So in this case, we're only going to have one type of interaction in our network. So this would be like a functional connectivity matrix here. And we're going to have basically a stack of these networks. So each of these different stacks is going to represent some different state or different point in time of our system. And we're going to use these interlayer identity links to link nodes between these points in time so that we can understand how our system evolves throughout time or task. All right, so we can have two types of these types of networks. You can think of one for temporal data, in which case time matters. We have a sequential sequence that we're studying. And you can also think about having categorical data. So maybe this would be something like a task network where it doesn't really matter the order that you look in. You have something that changes between conditions, but if I say 1, 2, 3, that's equivalent to 2, 3, 1. All right, and so we're just going to link differently. In this case, we would want to link a node to itself in every single instance because the time doesn't matter, and we want to be able to understand the interactions between all of them. All right, so these types of networks are really nice for the type of questions that we want to ask in neuroscience, but they really haven't been used very much. But you can think that maybe you would want to use something like this to represent multimodal data, where you have data from structural imaging, you have fMRI data, you have MEG data, and you can use this type of framework to link together the different types of data you've taken. Or maybe you have different groups and you want to link the two groups in your network. The type of questions that I'm going to talk about today are more for fMRI data, where you have something like multitask data, and you have different recording periods of different tasks, and you want to ask, how do you move between these tasks, and how does the network change between tasks? Or something like temporal data, where we have a long time series, and we want to ask how our network structure evolves over time. All right, so for multitask networks, we can ask many types of questions. We can say, well, what if we have one period of recording from a rest state, and then we have multiple periods of task states? How is the network structure at rest different than the networks that we've extracted during the task states? Or how do the task networks differ from one another? How are they similar? How is the brain transitioning between the different task states? Or perhaps you have some sort of temporal network. Like I said, these are probably the most commonly looked at types of networks. And you can ask, how do these connections evolve over time? If we have some sort of learning data where we have recording from different periods of a task, maybe as a subject is learning a task, how is the network changing as the learning occurs? All right, so specifically, how would we do this? So this goes back to this idea of the sequential graphs and the multiplex networks. And so like I said before, each layer of our network is going to represent a single functional connectivity matrix. And so if we have something like a temporal network where we're just looking at a single signal over time, we're going to use this idea of these single inner identity links. And that basically gives us a sense of progression of time throughout our course. So I would say, okay, region 1 is linked to region 1 in the next time step, and in the next time step, and in the next time step. Or if we have multitask networks, in this case, maybe it doesn't matter that they did task 1 before task 2, they're interchangeable. So in this case, we're going to link region 1 to itself in all of the layers, all right? And so this is basically just what I said there. So for temporal networks, you first need to choose some sort of windowing scheme. And so you can do this in multiple ways. You can have non-overlapping windows, you can have overlapping windows. What really matters is that you choose some window that's going to represent the timescale of the interactions that you want to look at in your data. And so you need to know a little bit about your data to choose this type of windowing scheme. But once you do that, you're going, for each window, you create your functional connectivity matrix, and then you're just going to line them up in time and use these inner identity links to link each layer of the network. So you can still calculate many types of network statistics for this. So you can look using this multi-layer framework, and I've just listed the references here for some of these. You can look at things like degree. Essentially now, instead of doing these calculations on a matrix, you have a tensor, and so you need to do tensor math instead. But you can do this for degree, clustering coefficient. You can look at path lengths and walks. People have looked at centrality. But today I'm really going to focus on this question of modularity, because this actually allows us to define some new metrics that you can look at to study dynamic processes, and I'll give some examples from learning. So modularity, you might be familiar with, is one of the things that you can use to look at community structure in networks. So for functional fMRI data, what this means is that you're looking for groups of nodes that are more correlated with each other than within the group than between the groups. So you're going to get out communities where the members of the community have correlated dynamics within the group. And so one of the ways to detect these communities, you can use a modularity maximization. And the modularity maximization has been extended to this tensor analysis. If you're familiar with this, basically you have this extra term here that is giving you the detection between these layers. So you have your normal parameter, your resolution parameter. So this basically is something that you need to vary to look at the size of communities that you detect. Do you want to detect large communities? Do you want to detect smaller communities? And then this parameter omega here is related to this coupling between our layers. So this is going to give you the strength of the inner identity links between the layers. And so these are both parameters that you're going to need to choose when you're doing this type of detection. And you probably want to run your analysis over multiple parameters and look for regions of stability to pick these parameters. And you can do this using a Louvain-like greedy algorithm to do an optimization of this function. But one thing I do want to point out, and this is something that I think commonly gets overlooked when people are doing this type of analysis, is that in order to optimize, to find the to maximize the equation for modularity, you're basically looking at this energy landscape here, and you're looking for a peak in the energy landscape. But the modularity has many near degeneracies, and so the peak of this function, you can see there's many small peaks here, and it can get stuck in these local maxima. So you actually need to run this algorithm many times and do some sort of consensus partitioning to find the true representation of community structure in your network. And so I'm not really going to go into that more than to say I highly recommend that you read this paper here, which goes into a detailed description of how to do this, and I'll provide a reference to some code at the end, some MATLAB code that you can use to do consensus partitioning to look at the true community structure of your data. All right, so what does this mean when you do community structure across these multi-layer networks? Well, what it means is that now you have communities that exist both in terms of the regions that are in the community and their point in time. So you can see here I have two examples of, here's the nodes, so this is going to represent brain regions, and this is the layers of the network. So this is going to represent time as we're moving through the layers of our system. And what happens is, maybe it's a little simpler to see in this example here, is that initially in time you can see there are three communities. So the color here represents the community. And you have communities that can be born initially and then can die, and you have new ones that can start in the middle. So every member of your community, or your community here, is a region and its point in time in the system. All right, and now we can study how regions evolve and how they change their community allegiance over time, and we can use that to study the dynamics of the system as it evolves. And so that's what we're going to do. So now you can actually define two new measures that I have here called flexibility and promiscuity. So regional flexibility is just going to look at the number of times a region changes its module allegiance. So if it starts in one community, does it stay in that community throughout time, or does it change and does it go back and forth between communities? We can also talk about promiscuity. So this is just going to be how many communities does this region participate in? Does it tend to go back and forth between two different communities? Or if you found 4 communities total, does it go back and forth between all 4? And we can look at these measures to try and understand some of what's happening in the system as it evolves. So here's just an example here. So let's say this is your community assignment. You have 5 regions in this example, and you have 10 time points that you're looking at. And so you can see that in the first slice, everyone is in the same community except for region 5. And this changes over time, and we can find that there are, if we calculate both the flexibility and the promiscuity, region 1 is very consistent. It stays in the single community the whole time. So it's going to have low flexibility and fairly low promiscuity. But that's very different than, say, region 4 here, who not only participates in all of the communities, but does a lot of switching back and forth between them. So he's going to have high flexibility and high promiscuity. And you can have different combinations of these depending on the dynamics of the region. And then we can talk about the overall flexibility or promiscuity of the network just by averaging over what all of the regions are doing in the network. So another thing you can look at is something called the module allegiance matrix. And so what this is actually going to measure is the probability of 2 regions being in the same community. All right, and so the way that you would calculate this probability is you're going to make a bunch of contingency tables. So basically, a contingency table, you would just take a single layer of your network, and you would say, okay, well, in this layer were regions 1 and 2 assigned the same community. So we can go back to our example here, and we can say, all right, well, in this first time slice here, we're going to put a 1 if the regions were in the same community, and we're going to put a 0 if they were not. So in the first time slice, you can see that regions 1, 2, 3, and 4 were all in the same community, 1 and 5 were not, and we're going to put a 0. And we can build one of these contingency tables for every single layer in our network. And then what we can do is we can average across all possible contingency tables. So you can have multiple dimensions that you're looking at. So maybe you have many time or tasks, so these are the layers that we were talking about, these sequential graphs. Maybe you have multiple subjects that you've done this over too, and you have all of the multiple optimizations, because remember, like I said, we need to run this algorithm many times to do all of the possible ways of doing community detection. So you can average these contingency tables over all of your possible variables and end up with something then that gives the probability of 2 regions being in the same community. And so here's an example of doing this with some learning data. And so you can actually see here, so the reds are going to be there's a high probability of these regions being in the same community, and the blues mean there's a low probability of them being in the same community. And you can actually see that there's this block-like structure here, and as it turns out, these 2 blocks correspond to the motor system and the visual system in this data. So you can actually see that regions within the visual system tend to be grouped into the same communities. Regions within the visual system seem to be grouped within the same community, and they're not within, there's a low probability of them being within each other's community. So this also allows us to define some more measures that we can look at. So we can look at 2 things called recruitment and integration. So recruitment is just going to be, let's say that we have some sort of higher classification of our systems now. We know what regions are in the visual system. We know what regions are in the motor system. And so we can look at the matrix and we can say, okay, well, these regions are in the visual system. These are in the motor system. And recruitment is just going to be the strength of the interaction within a group. So we're going to look at this modular allegiance matrix and basically calculate the average probability of these regions being in the same community. And then we can also talk about integration. So that's going to be the strength of interaction between the groups. So that's these off-diagonal elements here. And we would just take the average value here, which is looking at the probability of these inter-regional interactions. So are they likely to be in the same community? All right, so how do we use these types of measures to look at neuroscience data then? So I'm just going to go through a few quick examples to do this, and these are all in relationship to looking at learning data. So in this case, subjects they were doing a very simple motor task, looking at music cues and having to press buttons. And so there's data from 3 different sessions as they practiced this task. And you can ask things about flexibility then in relationship to learning, all right? And what was actually shown was that if you looked at the flexibility during the first session and compared that to the second session, you saw that there was an increase in flexibility, whereas between the second and the third section, there was a decrease in flexibility. But what's really interesting is if you look at the prediction, you could see that if you measured flexibility in the first session, you could predict how well the individual would perform in the second session. And if you measured flexibility in the second session, you could predict how well the individual would learn in the third session. And so that's data shown here. And so what they saw was that actually if you had a high amount of flexibility, you were more likely to learn the task, or you performed better in the task. And you could actually predict that just from looking at the flexibility in the initial stages. And this has also been used to look at core periphery structure in learning networks. So again, this was subjects doing a learning task, and what they saw was that the flexibility actually increased as subjects were learning this task. And you could look at different brain regions here. I think there was 112 brain regions that they studied here. And if you looked at the flexibility of the brain regions, you could see that there were some that had a very low flexibility, some kind of in this intermediate range, and some with a very high flexibility. And so this actually formed a core periphery type network. And you could see that there was a very stable core and a very flexible periphery. And you could actually then make predictions about learning based on the shape of this curve, essentially. And so how flexible were different regions, and how did they transition between being stable versus flexible? And you could use that to make predictions about how the subject learned the task. And so finally, I just want to give an example of this recruitment and integration. And so here is an example of, again, looking at learning a motor task over time. And there were 4 different sessions in this case. And you can see, if we look at, this is what we were looking at before, this integration. So the recruitment is going to be the block diagonals here, and the integration is going to be these off-block diagonals. And you can see that there's a decrease in the integration between the visual and motor systems as the individuals learn the task. And what was very interesting about this is you not only have this decrease, so you have this decoupling of systems essentially as the subject learns, but you could also, if you studied the integration of these non-visual and motor systems, or actually I believe the recruitment of the non-visual motor systems, you could again predict the ability of the subject to learn the task. And so basically this is all just to say that there's lots of questions you can answer with this. I've just given a few examples here of the types of things you can look at, but by looking at these measures, we can try and understand some of the mechanisms here of the decoupling of systems as subjects learn. We can make predictions about the ability of subjects to learn over time. So I just want to leave you with some useful references for this type of analysis. There's a very nice introduction to multi-layer networks here. This is a more general sense. It's not related to neuroscience, but it gives you a nice description of multi-layer networks and how to use them, the types of questions you can answer. These 2 papers are related to community detection in networks, and so these are great resources. And here, probably the most important thing I can leave you with is MATLAB code. So if you want to do community detection, this is a great resource for an algorithm that does the multi-layer community detection. And then I want to say that this is a toolbox. The paper that goes along with this toolbox, so this is from our lab, is not published yet. So proceed with caution. If you have questions, please feel free to email us. But there's code for looking at flexibility, promiscuity, and the recruitment and integration if you're interested in those types of measures. All right, so I think that's everything. I want to say thank you to our many funding sources. Hopefully I've named our multiple collaborators as I went through the slides. And I just want to say that, as was mentioned, I'm moving to Buffalo, and I'm looking for postdocs. So if any of you are interested in this type of network analysis, please contact me. And that's pretty much everything. Yeah. Yeah, can you? Okay, she's going. I don't think it's on.
To search this solution of the community, actually greedy algorithm is kind of easily falling down into local optimal solution. So, however, the measure you used later quite depends on this algorithm you used. So have you considered use other algorithms like something like simulated annealing algorithm, which can search this?
So you certainly could use a different algorithm to search it. The code that we use doesn't. It uses the Louvain algorithm. It's largely a matter of the time it takes to run various algorithms. So this is a fairly fast algorithm, and if you run it multiple times, you can see that while there's some variation between them, depending on your data, you're going to get largely similar results. But that's why it's very important to run the algorithm multiple times. And we would recommend something probably around 100 iterations, or not 100 iterations, 100 different instances, and then use the techniques that are in this paper here to do some sort of consensus partitioning that says, okay, now that I have my 100 different representations of this network, how do I combine them to come up with some sort of overall representation of the structure? But you're right, you can use a better algorithm, it's just going to be less efficient in terms of time. So it depends on how you want to think about the problem.
Yeah, just to avoid falling into this local optimal solution, right?
Right, you're just trying to maximize the quantity, and you can choose how you want to do that. Yeah, absolutely.
Okay, thank you.
Hey, thank you. Great. coffee break. Let's come back at 10:40. We'll start again then. Thanks.